Okay, we have a pan of water that's at 100 degrees Celsius, and then we switch off the heat, and then we imagine the temperature of it going down and slowly going down. What's it going to cool down to? Well, it's going to cool down to room temperature, isn't it? We'll come to that idea in a moment. Right, given all this information, then we're asked to write down the value of A. Well, the piece of information to spot is that the whole thing starts at 100 degrees Celsius. So in other words, when it starts is when little t is 0. So we know that basically this. We're using this fact: when little t is 0, when time is 0, temperature is 100. And therefore if you substitute little t as 0 in here, e to the power 0 is 1. So the whole thing, if I try and cover that bit up, you get big T equals 25 plus a, and therefore little a must be 100. Sorry, forgive me, little a must be 75, because 25 plus 75 gives you the 100 we want. Part 2, state what the value of 25 represents in the equation. Well, you've got to think, over a long period of time, what's the equation going to do? As little t gets very large, big T is going to tend to 25, isn't it? Why is that? Well, think about this equation here. As little t changes, the 25 is just going to stay as 25. What's going to happen to the value of this expression? Well, let's imagine that little a is just 1 for a moment. So we're just dealing with e to the power of negative something. Well, e to the power of negative a million is almost nothing. It's basically 0. It's extremely small. So what I've effectively done there is I've let little t become very large. And e to the negative of a large number is 0. So the whole thing, eventually this term will disappear and big T will reach 25. So that must be room temperature. 25 is room temp. Now, when the heat is switched off, the initial rate of decrease of the temperature of the water is 15 degrees per minute. It seems like quite a lot of information to take in there. Just before we continue, since I now know the value of A, I'm just going to write it here. So instead of using this as our base equation, we're going to use this slightly more improved one, where we've got the value of A here now. Okay, there's the word we need to zone in on. If we're dealing with the rate of change of temperature, we know we need to do d big T, d little t. That's the rate of change of something. Now, let's think about how that works. If you differentiate 25, it disappears. If you differentiate this term, when you do e to the power of something and differentiate it, you just basically multiply the whole thing by the derivative of this bit here. So it's going to be minus k. So if that was e to the power 3t, you'd bring the 3 down to the front and times it by the 75. But then you don't change the power. But this is e to the minus k t, so we're going to bring the minus k down to the front. And then you still keep the e bit the same, you still keep the e to the power bit the same. So you're just going to multiply this term by minus k. Great, now we have our derivative. Let's think about the rest of that sentence. It says the initial, so when little t is 0, and it's a decrease, so we're expecting d big T, d little t to be negative, and it's going to be negative 15. So in other words, when little t is 0, the rate of change is negative 15. So we can set that up as our equation. So I've just put minus 15 here for this, and I've substituted little t again to be 0, which will just make this bit 1. So minus 75k, and then that gives us the value of k. I think that's a hard question, so go back over that if you need to, that part 3. Part 4, find the time taken for the temperature to drop to 45 degrees. Well, again, I'm just going to look back up here. Now that I've got the value of k, I'm going to improve this equation even further by writing the value of k in there. So we've got a proper full equation now with no unknowns in it. And then I just need to set the temperature to be 45 and solve it for little t. So let's do that. So, great. Okay, how do we solve that? Well, I'm first going to take away 25 from both sides. I don't have much space here, so bear with me. Then I'm going to divide by 75. Then I'm now going to ln or natural log both sides of the equation, which will bring this sort of power down. It gets rid of the e. It brings this power down to sort of ground level. I need to use natural logs because e is the base. Now I've run out of space, so what I'm going to do here is I'm going to times both sides of this equation by -5, just to leave little t on its own on the right. And then I'm going to type that into the calculator, and we'll get little t is 6.61 minutes. And then the last question, second pan of water is heated, but the heat's turned off when the water is, let's say, at 80 degrees Celsius. How would we change the equation? Well, I think it's quite a straightforward question, really. Well, here, how did we work out that this was 75? Well, it was 75 because we started at 100 degrees, and we needed this to be 25 plus 75 to make it 100. So if we're starting at, say, 80, then we'll just make this 55 instead. So the answer I think they're looking for there is just to say, use a smaller value of little a. And then I've given an example then of the equation that I might use.